In the previous video, we measured the performance of reference types and value types. In this video, we'll demonstrate a compiler optimization called generic specialization. In Section 2, we saw how generics can afford us maximum code reuse. There is, however, a caveat to generics that I've yet to mention. The Swift compiler is able to optimize methods based on their types. However, with your compiler optimization set to none or even fast, the Swift compiler cannot optimize a generic method since the incoming object can be of any type. Generic specialization is a compiler optimization that is afforded to us by whole module optimization. Since whole module optimization compiles the entire module rather than a single code file, the compiler is able to infer the type and perform any necessary optimizations that the type is eligible for. Let's create a new Xcode project. Make it a single-view application with unit tests. Once your application is loaded, we'll create a new file which we'll name genspec. We'll define the two methods we wish to test. The first we'll call intMax, which will take two ints, x and y, and return one int. Our return statement says, if y is greater than x, return y, otherwise return x. Now, we'll create our generic version, which we'll name generic max. It will take a type t that conforms to comparable. Our generic max will take two generic parameters and return an item of the same type. Other than that, our methods will be identical. It's important to note that our test suite is a different binary, so whole module optimization won't optimize our functions if they are called directly from our tests. So in order to measure our generic function properly, we need to create two wrapper functions that return the result of our custom functions. I'll create one function named generic intMax, which will take two ints and return one, and then simply return the results of our generic max function. We'll do the exact same thing for our non-generic intMax function. Now, we'll be able to test our operations with whole module optimization. Navigate to the test class and add a property named genspec, which is of type generic test. Then, in the setup, we'll initialize our generic test object. We'll make sure to set our genspec to nil in our teardown. Let's edit the name of our test to test generic performance. And then, inside the measure block closure, we'll add a for-in loop that iterates over an array from 0 to 10 million. Inside our for loop, we'll call our generic test instance and call our wrapper method, passing in two random numbers. If you'd like a more concrete test, you're welcome to use two hard-coded integers if you like. Next, we'll simply copy this test method and change the name to test non-generic performance, and switch the method that we're calling. If we run each test now, we should find that our non-generic function outperforms our generic int function. Which, as expected, is precisely what happened. So here's why. In order for our generic function to be able to handle any type, the compiler is adding some needed code to our function at runtime. With whole module optimization turned on, our compiler will use a special optimizer called generic specialization, which will help our generics to infer and optimize for the incoming type. So let's turn whole module optimization on now. We'll head over to our build settings and filter our results. We'll change the debug optimization from none to whole module optimization. Now, if we run each test, not only will we see an enhancement of overall performance, but we should also see very similar results between our generic max function and our intMax function. And this is exactly what we get. Again, this is a good opportunity for you to go back through the code you've written in the past and measure the performance with whole module optimization turned on. In this video, we have seen how to improve the performance of our generic functions through generic specialization. In the next video, we'll introduce some algorithms and Big O notation.